Okay, here we go.
easier.
So we're going to be done with this quick.
It
All right, so
I'm
I'm planning on giving you guys some work time today. You take advantage of it. If not, we'll just do some more calculus. Come on. Okay.
Can we
I
just
wanted
choose
to
to have
give you-
fun option?
Okay, let's focus. We're all together.
I'm sorry.
Oh god. Pepsi tears up my stomach.
Okay. How about if I take the limit as x approaches 2 of f of x here? Okay, I heard can't be done.
Can't it?
It's all right.
I think it can because it's filled in. Because you wouldn't have.
Yeah, but it's
Okay, so you guys are still thinking like
you'd have to
pre-calc.
build up. You'd have to move
You're
your
still
thing.
thinking
Well, you can
about
find-
evaluating. We're not in that land anymore.
Well, I guess it can because it's approaching it. You don't want the exact spot.
Yeah, it
you
can be
want.
done.
Okay, so I heard some things that show me that you know some pre-calc, definitely, so that's good. Because people were saying, Austin, I think, said something about like, oh, but it actually is there still, so it's okay. That's the pre-calc conception, right? Of a function. It is defined there, correct? So yes, f of what?
F
2
of 2
is, looks like,
Let's just say 8.
okay, I'll buy that. Looks a little bit too much, but I'll buy it.
But is f of x approaching?
Is this what this is asking?
No.
It's not the same question at all. This says as you approach 2. Do we have that?
Yes.
Does it exist?
Yes.
Yes. What is it?
Approaching 4-ish.
3.5.
3.2, whatever. Okay, I drew it. My drawings aren't perfect. We know this.
Because you go
It's
up
on the
three
line.
Pretend that's here. Here we go.
Oh, okay.
Ah.
Oh, okay.
Okay, when we talk about limits, what's the limit of something? What is the value of something? And what is something continuous, which we're going to do here soon. Those are 3 separate things. Value, limit, and continuity are 3 different things. I, in calculus, used to get confused about especially limit and continuity. So we're going to go over that again, but they are not the same thing. The same rules do not apply. They're different things, okay? Different types of animals, if you may. Okay, so what are the 3 ways yesterday? Let's summarize real quick. 3 ways that a limit can't exist, because these are really the only 3 for anything that's limiting behavior. This extends from Calc 1 all the way up.
There's that kind of jump. Where
There can be a jump. Let's say that more generally. So this is ways a limit. So I gave you a picture yesterday, but ways a limit can't
You
or
told
does
us
not
last year if you have to lift your pencil, right?
Yeah.
does not exist. Yes, that's a rule of thumb for not limit, but continuity, and that's the informal definition. But
Because
that's
for
not
like
limit,
this one, technically you'd have to move your pencil.
right? But that's continuity.
Yeah.
Okay, so it's something else. Real easy to get them mixed up, and I used to get them mixed up, so I know it can't be mixed up. So you guys said a jump. One way a limit doesn't exist is a jump. So we'll say that jump. What's that really mean though? Because there's other
It's like a
things.
piece when you're approaching a point from like a different point from both ways, like
Like you're going
this way's
two
going
different
like
directions.
up and this way's going
So you're
down.
approaching something different when you're coming from the left versus when you're coming from the right. That's it. Good. Thank you, Anna. When you approach, because what's the key word with limit?
So then we're done.
As you approach.
When you approach from the left, it is different than when you approach from the right. So if you just want a quick check, jump is a good way to think about it. We're not just going to do quick checks in this class, though. I'm not going to give you an AP doesn't have this in the curriculum. They don't have the full analytical definition of a limit. I'm going to show you what it is just real quick so you have an idea. It's not in AP's curriculum, which is good because it's difficult. But there is a more rigorous version of a limit. So we've just been talking about like approaching, using these imprecise terminology. There's a much more precise definition. So we'll see that in a second. Okay, before we do that, What's another way a limit can't exist? Asymptote. Okay. What's that really mean?
Infinity.
When a line.
Infinity is involved. I like
It
that.
doesn't approach a certain point.
Doesn't approach a
It
certain.
approaches
Let's not say point. Let's say. Because that makes me think of a
value.
sequence.
Value.
A certain value. A certain x value.
Y.
Or Y.
Isn't it a y value we're looking for it to approach?
Yeah.
When we do a limit, don't we always have like the limit and what's underneath?
X.
X approaches something. We're looking to see if it's equal to a specific y value, right? So
Could
that's
you
what
do
we're
a limit as Y approaches? Can you do that?
Let's say does not, you could, yes, does not approach a specific, can I spell specific? I don't think so, I'm tired.
It's like Pacific.
Specific
It's
value.
not.
But it's not.
Now Austin asked, could you do that with like a y value? Yeah, but then you're in 3D land and then we're gonna have to be talking about why we're on a surface. And that's gonna get a little bit more iffy. And it's hard for me to draw. Like drawing in Calc 3
I probably wouldn't
sucks.
understand.
It just sucks. That's the cool part about Calc 3, visualizing things in 3D lands. So, I really
That's what
like
my
it.
dad talks about.
It's hard to do though, and really hard to teach. Like my teacher, he just never drew stuff. He's like, oh, you guys got it. And like everyone failed the class. He was a great teacher though. He got me to be a math major. He was the one. He was an old school teacher from the University of Michigan, like super big researcher. He was retiring out here. Good guy though. Anyway, sorry, tangent.
You're
Ha ha ha!
Why?
Calculus
Why?
joke again. You guys don't get my
Oh,
calculus
No,
jokes.
do you want to hear my joke from me?
So when someone says go off on a tangent in the future,
We
right?
mean
You're
go
gonna know
off
what that
the
means.
circle.
Yeah.
Okay.
You mean
Miss-
go off
Miss
the
Mickey.
circle or go off the
Curve.
curve? Okay.
I
Okay, Miss
Already,
Me, what is
because
Matt's
Jacob
favorite
went off on a
food?
tangent about going off on a tangent
I know.
one time.
Miss
so.
Miss Me, what is Matt's favorite food? Pie.
What's the third way? I'm done with tangents.
It's when it jumps back and forth, but never.
What do we call that? Oscillate.
Oscillate.
Thank you,
Like a
Is that an eye?
Mr.
Oh.
Rodney.
That is not
Oscillates.
how
Why
it
is this one? Because some of us, I still think, have an issue with that. I think we're still confused about this. Who's confused about this a little bit? Anybody want to admit it?
Truthful.
Wait, I'm sure I am. So.
Not me. Remember, if you're, think about it like this. Let's say we've got the XY axis, because this has big
Basically, just
implications
stops
in Calc 2.
approaching, doesn't it?
Let's say that we have a function and it's bouncing back and forth in a corridor.
Between 3 and 5.
Between wherever, yeah, exactly. So let's say we've got it bouncing. First it's bouncing pretty slow, then it starts to bounce faster and faster and faster and faster and faster and faster and faster when you get to a certain point.
And eventually.
Over
it's
here,
not-
can you find the limit value?
Yeah.
Yeah, anywhere that's like it's clear where you can see the function, you can actually find a limit. It's just whatever its x or y value is. It's whatever its y value is, correct?
But when it's oscillating that fast.
But if it
it's not
starts
approaching.
bouncing really, really fast, if it starts bouncing infinitely fast, and there's a lot of times where this does happen in real life. This isn't just like someone invented this, right? This is real life where this does happen in nature. Then you can't decide once you get really close to this, and this is perfectly to our analytical version. Once you get arbitrarily close to here, you can't decide where you're at anymore. You can't decide if you're, as your x value gets arbitrarily close to this, what do you want to call it, Anna? You were
5.
mistaken. Let's call it 5, okay? As we get arbitrarily close to 5, you can no longer make that decision on whether the limit is up there
Or
down there.
Is there?
So since it's not, then it goes kind of back to this logic, right? Since it's not approaching a single thing,
It just doesn't exist.
It just doesn't
Technically
exist.
an answer, and it's just we can't find it.
no,
Or
it's
there
trapped
actually
between that
is
corridor.
no-
The best you could do is say it's between, let's make up numbers here, 4 and 2. That's all you could say.
So
Now,
there's no
that's
way you
useful
can find
information, and you can use that information. A lot of the Calc 2 arguments use that information and say, okay, so it's between 4 and 2, so now I can go do this.
But like in a
But you
calculator
can never
sense,
get it. You can never pinpoint.
If
But
you-
right, like if you're trying to decide that, you can't decide. It's between 4 and 2, I don't know where.
if you got to x equals 5, like in a calculator sense, couldn't you just zoom in so much?
Try it.
I don't really feel like doing that. I'm just
That's a
asking
really
you.
interesting
Because
question. Here,
there's
try
so-
this. Sine of 1 over x is one where this happens at 0. As x approaches 0. Try to zoom in on your calculator to try to answer that question.
The reason why you won't
I
be
think
able to zoom in.
Is it in the book though?
Yeah, it's one of the problems.
Well, I just turn my
I know the answer now.
The reason why it won't zoom in that much is because there's infinite numbers between those two x values. So you'll just see a bunch of lines still.
Exactly.
Like you can't zoom in close enough.
Yeah, exactly. And also another point, good. Another thing is, do you think your calculator is actually drawing the real object? Is your calculator, let me ask you this, because this may seem like a strange question, but I need a calculator. It's more dramatic.
What the heck?
I can't believe I have energy left. It's been a long day.
Yeah, how did that
Okay,
happen?
to make this more dramatic, is your calculator a window? Is it a picture of reality?
No, it's kind of a.
It's not a window into reality, is it? Or a picture of reality as it actually exists? What is it?
It's like a
It's just a graph. It's just helping us understand.
When you graph something like the sine of 1 over x, what's it doing? It takes points, and depending on, you can tell it to change, use more points or use less points, and it connects the dots between those points. So it takes values, plugs them in, plots them, and connects the points.
Eventually just
You can actually turn this on and off. If you go to mode, right? If you go to mode,
Go away, fly.
have you guys ever seen that thing on mode where it says connected and dot? You can actually change it so you can see the actual points it's using to connect the dots. So in other words, your calculator doesn't use functions. It's not part of this calculus land that we're learning. It's part of sequence land, which is Calc 2. It's not part of functions. It doesn't plot functions like we know from our library. It uses sequences and approximates functions. So, little tangent there, but it's a good tangent.
I just don't understand.
It looks like
Well,
a
you
bunch
shouldn't
of.
tell the way.
It does. It just
But.
like keeps. I know. It keeps going up and down. I was like, what? I don't know.
Okay, last thing for today. We've had some good discussion here. I think we're understanding better. Okay, this is the rigorous definition of a limit. This was developed much later. When was calculus invented again?
The 1600s.
Mainly 1700s.
Later, early 1600s.
Late.
Isn't that like
Late 1600s is when calculus was invented. Do you think this epsilon delta definition of a limit, or even a limit, they didn't even have limits, right? Limits didn't come around until Cauchy and those guys, 100 years later, late 1700s. And those guys still they started to look at this epsilon delta definition, but this wasn't totally made concrete until the early 1900s even. This is the most modern math you've learned by a lot. This thing I'm going to show you right here. This is a much, much, much more precise definition of a limit, and this is what you do in analysis courses. And it may seem really difficult right now. It's also really cool.
Okay.
But it's good to see it. AP doesn't do this. They want you to be, they know everyone's not going to be a mathematician. They're training people to be engineers, take engineering courses, training nurses, doctors, everyone. So they don't think you need to see this, but I'm going to show you.
It's like, well, let me open this up.
AP's a lot broader, right? Okay, so let's say we want to talk about the limit at C. So we're thinking of, we'll call this function f, and we want to take the limit as x approaches C of f of x. What's it mean? Does it look like we're going to be able to find that limit, by the way, just looking at the picture?
Yes.
Yeah, we should be able to find it. There's nothing fishy. None of those three things. It's going to equal some L. In fact, let's just draw that L, shall we?
Sure.
So do you guys agree that that's going to work out?
Yeah.
What's that really mean? We've been talking about it, but we really haven't been that precise. And that's okay, because you can get the idea without being super ultra precise. But here's really what it means if you're going to take it and do more advanced stuff with it. Okay? So let me just whack. Here's what it means. I'm just going to write it down, then we're going to talk about it. It means for each epsilon greater than 0, it's another new Greek letter. I won't use all the symbols. You can write all this in symbols. There are math symbols for all of these words except like A. There's a symbol for there exists. There's a symbol
What is
for each.
the?
The that doesn't have a symbol, but these have symbols. There exists a delta greater than 0 such that
Wait, that's your delta symbol? I thought delta was the triangle.
these Greeks are just, That makes no sense.
Of course it doesn't.
Just misery,
This is fun stuff. Don't cry.
You will like it.
You might not, but I do. So I'm going to draw some other stuff in here. Let's see. It's purple. Our book does have these in them. Maybe I should give you guys.
There's Mr. E. There's one on page 54.
Awesome.
I think this really does help you, seeing this, help you understand precision of a limit, though. Limits aren't these vague quantities, they are very precise. They seem vague, though. Okay. Alright, so let's try to read this nonsense now, this nonsensical Greek stuff.
Is that C minus F?
C minus.
Delta.
Okay, C minus delta. Okay.
I've never been good at writing deltas. Sorry. Okay, so let's read this. So we all are comfortable with this statement. We know what it means a little bit, right? We got an idea of what that means. We're just saying as we write along the function from both directions, the limit, it does look like it approaches some value, and that's the value, the L. Okay? What's that really mean, though? This is called an epsilon challenge. For each epsilon greater than 0, you can kind of think of this as a game. Someone's challenging in you and saying, I'm going to pick an epsilon, like epsilon equals 0.1. And I'm going to say, okay, for epsilon equals 0.1, here's what you got to do. It says for every epsilon, no matter what challenge you're presented with, there exists, it has to be there somewhere, a delta bigger than 0 such that if you're between, if the value that you pick, your x number, if the distance between it and c, so I'm going to pick an x that's close to c somewhere, like right there. Okay, there's my x that they're talking about. The distance between x and c, if that's less than delta, if that's between less than delta, you don't even have to think about this too much yet. If that's less than delta, then here's the punchline.
Punchline.
Okay.
I got it.
If that is in this neighborhood, if it's between here and here, and that's what I did, is I bracketed it with a C plus D so that it would definitely do that. If it's in there, then there is absolute certainty, if this limit exists, there's absolute certainty the difference between f of x and L. So if I trace this up, and I find that's f of x, right? The distance between f of x and L, that's this, right? Right here. That has to be less than epsilon.
It actually kind of makes sense.
So it says, let's see it again, because this is really deep. This is probably the deepest thing you've ever learned in math, by far. For each epsilon greater than 0, there has to exist a delta. There has to exist a delta. You can find a delta so that your delta might be this far out.
So delta's just any.
You know, like delta's this distance, right? Right here.
Okay.
So delta might be that far out, or you might have to make it this big. But it says every time this happens, if you can find a delta that does that, then this has to be captured. That's what has to be true for the limit to exist. This x is in between here.
So like
and here.
with your thing equals 0.1, whatever that is, the f of x minus L is going to be less than 0.1.
Yes.
Yeah.
And what I'm going to do, I'm going to let this sink in just a little bit. I'll do an example problem like this on Monday, just to give you an idea of what this is like. So we'll take an epsilon challenge and we'll show that it actually works. But if a limit exists, it has to satisfy this kind of epsilon challenge. And notice it says for each, you can also use the term some books. I even like this probably a little better. For every, that means no matter what epsilon challenge they give you, if the limit actually exists, you got to be able to make this work. You got to be able to find a delta neighborhood. You get to pick the delta.
But what do you mean delta?
Hold on. They pick the epsilon, right? Like your opponent, you can imagine, picks the epsilon. The idea is this: if the limit exists, you've got to be able to come up with a delta so that you can make this wide enough so that it gets captured in their epsilon. So they make epsilon 0.1 here and 0.1 here. That's their epsilon, okay? So they made that 0.1 and 0.1 up and down. So then your challenge is to show that, yes, I can come up with a delta so that when I do x, it's going to land in between there. So if they come along and give you a different epsilon, a smaller one, so they say, ha, I'm going to try to stump you. I'm going to give you a smaller epsilon, like epsilon equals 0.001, and make this thinner. You've got to say, well, I'm still going to be able to find a different delta so that I can shoot this guy up in there and it's still going to work.
Is it like a midpoint? Is that what you're finding?
It doesn't always have to be in the
Or just
middle. That's a
anywhere.
good question,
Okay.
really good
So
question.
in that example, your
Like this guy could be near the edge. All I'm
Okay.
saying is that I get to pick the delta
It just
so
has
that I
to be
can make
between
this
them.
guy fall in between that neighborhood that you gave me, the
so
challenge.
so
that
you can
gave
pick
me.
whatever delta you want as long as it falls between 0.1 and 0.1 in that example.
Right.
Does
There are
this,
some constraints. The way this is set up, like you have to pick your delta really carefully.
Does
But
this-
if you can do that for every epsilon, then a limit has to exist. Okay? Can we see that there's a lot of precision here? It's complicated,
Yeah.
definitely. This is very logically complicated, very, very much. So if you're having trouble with it, that's fine.
Does this-
Everyone's going to have trouble with this almost when they see it the first time. But it's interesting, and I think you should see it. To see that, yes, there's more substance behind that limit. Okay,
does
that's
it
it.
work for anything?
We're done. If the limit exists, you've got to make it work. If the limit doesn't exist, then you can't create this different
It becomes like a solid or something.
I'm like,
Maybe I can do